For any help-related queries, call us at +1 678 648 4277. You can mail us at support@mathhomeworksolver.com or reach us at https://www.mathhomeworksolver.com. Problem 1. Consider the space of three-component vector fields U, X, on some finite volume 3D domain omega subset of R3. One linear operator on these fields is the curl nabla times, which is important in electromagnetism, which we will study in more detail later in 18.303. Define the inner product of two vector fields U and V by the volume integral U, V equals UV, omega. A. An 18.02 exercise. Derive the identity nabla U times V equals nabla times U, V minus U, nabla times V. B. Figure out how to do integration by parts with the curl. Show that U, nabla times V equals nabla times U, V plus W ds, where ds is the usual outward surface normal area element, and the W nabla U, V plus W ds, where ds is the usual outward surface normal area element, and the W appearing del omega in the surface integral over the boundary, del omega, is some vector field to be determined. Hint: use the identity you derived in the previous part, combined with the divergence theorem. C. Give a possible boundary condition on our space of vector fields such that nabla times is self-adjoint with this inner product. Boundary conditions can only involve one vector field at a time. No fair giving an equation that relates U to V. You should not have to specify all the components of U on the boundary. It may be convenient to define a vector field n, x, on del omega to denote the outward normal vector at each point on the boundary. Point 1. Mathhomeworksolver.com. D. Show that nabla times is self-adjoint for this inner product under either some boundary condition on U, similar to above, or some boundary condition on derivatives of U. Is it positive or negative definite or semi-definite? E. Two of Maxwell's equations in vacuum are where c is the delta c2 delta speed of light. Take the curl of both sides of the second equation to obtain a PDE in E alone. Suppose that omega is the interior of a hollow metal container, where the boundary conditions are that E is perpendicular to the metal at the surface, i.e. E times n equals 0. Point 2. Combining these del omega facts with the previous parts, explain why you would expect to obtain oscillating solutions to Maxwell's equations, standing electromagnetic waves, essentially light bouncing around inside the container. This kind of system exists, for example, in the microwave regime where metals have high conductivity, and such containers are called microwave resonant cavities. Problem 2. In class, we solved for the eigenfunctions of nabla2 in 2 dimensions. In a cylindrical region, R is an element of the 0, R, theta is an element of the 0, 2 pi, using separation of variables, and obtained Bessel's equation and Bessel function solutions. Although Bessel's equation has 2 solutions Jm, Kr, and Ym, Kr, the Bessel functions, the second solution, Ym, blows up as R0, and so for that problem we could only have Jm, Kr, solutions, although we still needed to solve a transcendental. Mathhomeworksolver.com. Equation to obtain K. In this problem, you will solve for the 2D eigenfunctions of nabla2 in an annular region omega that does not contain the origin, as depicted schematically in Fig. 1, between radii R1 and R2, so that Figure 1, schematic of the domain omega for problem 3, an annular region in 2 dimensions, with radii R is an element of R1, R2, and angles theta is an element of 0, 2 pi. Mathhomeworksolver.com. You will need both the Jm and Ym solutions. Exactly as in class, the separation of variables ansatz U, R, theta, equals rho, R, tau theta, leads to functions tau, theta, spanned by sin, m theta, and cos, m theta, for integers m, and functions rho, R, that satisfy Bessel's equation. Thus, the eigenfunctions are of the form For arbitrary constants a and b, for integers m equals 0, 1, 2, and for constants alpha, beta, and k to be determined. For fun, we will also change the boundary conditions somewhat. We will impose Newman boundary condition del u equals 0 at R1 and R2. That is, for a function u, r, theta, in cylindrical coordinates, del r del u, r equals r1 equals 0 and del u, r equals r2 equals 0. The following exact identities for the derivatives of the Bessel del r functions will be helpful. Using the boundary conditions, write down two equations for alpha, beta, and k, of the form alpha e equals 0 for some 2 by 2 matrix E. This only has a solution when det E equals 0, and beta from this fact obtain a single equation for k of the form fm, k, equals 0 for some function fm that depends on m. This is a transcendental equation, you can't solve it by hand for k. In terms of k, which is still unknown, write down a possible expression for alpha and beta, i.e. a basis for n-e. MathHomeworkSolver.com. B. Assuming R1 equals 1, R2 equals 2, plot your function fm, k, versus k is an element of 0, 20, for m equals 0, 1, 2. Note that Julia provides the Bessel functions built-in. Jm, x, is Besselge, m, x, and ym, x, is Bessely, m, x. You can plot a function with the plot command. See the iJulia notebook posted on the course webpage for Lecture 8 for some examples of plotting and finding roots in Julia. C. For m equals 0, find the first three, smallest k greater than 0, solutions k1, k2, and k3 to f0, k, equals 0. Get a rough estimate first from your graph, zooming if necessary, and then get an accurate answer by calling the cp.optimize.newton function as in set 1, and also as illustrated in the Lecture 8 iJulia notebook. Note that there is also a k equals 0 eigenfunction for m equals 0, corresponding to the constant function, the null space of A with Newman boundary conditions, as in class. D. Because nabla2 is self-adjoint under u, v, equals uv, we showed in class, in general omega, that this is omega still true with these boundary conditions, we know that the eigenfunctions must be orthogonal. From class, this implies that the radial parts must also be orthogonal when integrated via our doctor check that your Bessel solutions for k1 and k2 are indeed orthogonal, by numerically integrating their product via the Quadratic function in Julia as in set 2 and as in the Lecture 8 iJulia notebook. E. Let's change the problem. Suppose that the domain is now 0 less than or equal to r of less than or equal to r2, and the operator is a equals c, r, nabla2 with c, r, equals 2 for r of less than r1 and c, r, equals 1 for r greater than or equal to r1. Suppose we impose Dirichlet boundary conditions u, r2 equals 0. MathHomeworkSolver.com. I. What is the form of the eigenfunctions? Define them in terms of Jm, Kr, and Ym, Kr, with unknown coefficients in the r less than r1 and r greater than or equal to r1 regions. Don't try to solve for the coefficients. 2. If we solve for eigenfunctions O lambda u equals, and u is everywhere finite, then what continuity conditions must u satisfy at r equals r1 in order for O to be well-defined and finite? If you combine these continuity conditions with the boundary condition at r2, you should find that the number of equations that you must satisfy matches the number of unknown coefficients in the previous part. 3. As before, write down a condition fm, k, equals 0 that must be satisfied in order for the above equations to have a solution. The roots of this function then give the eigenvalues. You would have to solve it numerically as above, but you need not do this here, just write down fm, which you can leave in the form of a determinant. Problem 3. The Bessel functions u, x equals jm, kx, from class, solve the eigenproblem. MathHomeworkSolver.com. On 0, r, where u, r, equals 0